What happens when the entire internet literally runs out of room? I mean, imagine building a city where you only planned for a couple billion houses. But suddenly, every single person on Earth wants a house, plus a smart car, a smart watch, and even a smart refrigerator connected to the grid. How do you deliver the mail? Well, today in this explainer on the fundamentals of IPv6, we are going to dive into the elegant, completely mind-boggling solution to that exact problem. It sounds a bit crazy, but the internet actually ran out of space years ago. The original system, IPv4, used a 32-bit address space, which gave us roughly 4 billion unique public addresses. Now, back in the 1980s, that probably seemed like plenty. But by the early 1990s, the explosive growth of the internet meant we were burning through that address space fast. In fact, by 2011, the Internet Assigned Numbers Authority had to hand out its very last large blocks of public IPv4 addresses. The well had officially run dry. So, you're probably wondering, if we ran out of addresses back in 2011, why didn't the internet just crash? Well, network engineers are pretty resourceful. They rolled out short-term workarounds, things like network address translation, or NAT, and classless interdomain routing, known as CIDR. These tools essentially let multiple devices hide behind a single public IP address, which bought us a couple of extra decades. But let's be clear, these were just band-aids. They were definitely not a permanent fix for a world exploding with connected devices. Section 1. Enter the giant, IPv6. To fix this shortage for good, the engineering community knew they had to think bigger, a lot bigger. They needed a completely new version of the Internet Protocol, built from the ground up. To really grasp the massive leap we took, you have to look at the math. When you compare the 32-bit limit of IPv4 against the 128-bit capacity of IPv6, the difference in scale is literally incomprehensible. We moved from a system that could barely support the human population to one that could assign an IP address to every star in the universe. I mean, just wrap your head around this scale. IPv6 supplies more than 10 octillion times as many addresses as IPv4. It provides enough unique addresses to solve our internet shortage for generations. You could give every single grain of sand on Earth its own IP address, and you'd still have plenty left over. But of course, this incredible size introduces a completely new problem. If you thought memorizing an old IPv4 address was annoying, imagine trying to deal with 128 bits. How on earth are network engineers, or even computers for that matter, supposed to read, manage, and type out these massive 32-digit sequences without totally losing their minds? Section 2. Taming the hexadecimal beast. If we tried to write a 128-bit number out in binary, it wouldn't even fit across a standard piece of paper. So IPv6 uses a hexadecimal format. The address is chopped up into 8 sets of 4 hex digits, which we typically call quartets. In this system, each individual hex digit running from 0 to F perfectly represents exactly 4 bits of binary data. That compresses the visual length significantly, but let's be honest, 32 hex digits is still a real mouthful. To actually make these addresses manageable, the protocol lays out 2 golden abbreviation rules. Rule number 1, inside any of those 8 quartets, you can just strip away the leading zeros. So if you have a quartet that reads 0001, you just shrink it to 1. Rule number 2, if you spot a long string of consecutive all-zero quartets, you can completely replace them with a double colon. When you apply these rules in the real world, the transformation is awesome. You can take a massive, clunky number packed with zeros in the middle, drop the leading zeros, and then crush that whole dead space of middle zeros into a single double colon. Boom! Suddenly you have a much shorter, readable address. Just keep in mind, you can only use that double colon once per address. Otherwise, the computer wouldn't know exactly how many zeros to put back when it needs to expand it. Okay, so shrinking the address is great for us humans. But here's a totally different problem. How do the routers actually parse these giant strings to direct internet traffic globally? Back in IPv4, we had subnet masks to help with this. So how exactly does IPv6 slice up the pie? Section 3. Anatomy of an address. Think of it just like a physical mailing address, where the postal service uses a zip code for your city, a street name for your block, and a number for your actual door. An IPv6 address naturally breaks down into 3 logical chunks. On the left, you've got the global routing prefix. That's the big network block assigned by an internet service provider. In the middle is the subnet ID, used by internal network engineers to divide things up. And on the far right is the interface ID, which uniquely identifies the specific host device itself, like your laptop or phone. Now, what's really brilliant here is that the interface ID is strictly locked at 64 bits long. Because of this, engineers ensured that calculating subnets is incredibly uniform and straightforward. You don't have to deal with complex bit-level math anymore. You literally just change the subnet ID, and every single subnet automatically has a massive 64 bits left over, which is enough room for millions and millions of host devices. Section 4. Public, private, and local. Now, you might be thinking, what if I don't want my devices publicly accessible to the entire internet? Well, just like IPv4 had private address spaces, IPv6 allows for private networks too. Global unicast addresses are your public face, but unique local addresses, which always kick off with the hex digits FD, are kept strictly internal. They're completely unroutable on the public internet, giving you a totally secure space behind your company's walls. And then there's something absolutely brilliant called the link local address. Every single IPv6 interface automatically generates a link local address that starts with FE80. The catch? This address is entirely restricted to the local wire. It never passes through a router. It exists for one reason, so devices sitting on the exact same physical link can instantly talk to each other, zero external configuration required. But this actually creates a really interesting mystery. Back in the old IPv4 days, we used the Address Resolution Protocol, or ARP, to basically shout over the network and find the physical MAC addresses of our neighbors. But IPv6 completely ditches ARP. So how do devices actually physically find each other on the local switch now? Section 5. How IPv6 neighbors talk. To solve this, IPv6 introduces a brand new system called the Neighbor Discovery Protocol, or NDP. NDP operates using ICMP version 6 to seamlessly handle all local communication. Instead of relying on that old, noisy IPv4 broadcast traffic that interrupted literally every device on a network, NDP uses highly targeted multicast messages. It's kind of like walking up and whispering directly to the specific people you need, instead of using a megaphone in a crowded room. This whole system relies on a really slick 4-part messaging structure. Devices use neighbor solicitation and neighbor advertisement to figure out each other's MAC addresses. And it gets better. They use router solicitation and router advertisement to automatically locate their local gateways. A device simply powers on, sends out a router solicitation essentially asking, "Hey, any routers out there?" And the router instantly replies with an advertisement detailing the network prefix. But here is the absolute superpower of NDP. It's called SLAC, or Stateless Address Auto-Configuration. Using those router advertisements, devices can literally build their own unique, globally routable IPv6 addresses totally automatically. They take that network prefix handed out by the router, mash it up with a unique interface ID they generate on their own, and boom, they're online. No DHCP server required whatsoever. Think about how much of a game changer this is for modern networking. When you combine this massive address space with targeted multicast communication and built-in auto-configuration, it becomes clear that IPv6 isn't just bigger than IPv4, it's profoundly smarter. It is completely self-sufficient and dramatically reduces overhead for network admins. We've covered a massive amount of ground in this explainer today, from 128-bit hexadecimal beasts to the absolute magic of the Neighbor Discovery Protocol. Actually, I highly encourage you to go look at your own device's network settings right now. Whether it's your laptop or your smartphone, there's a very good chance you'll see a massive 128-bit hex address quietly sitting there in the background. The internet didn't just adapt to the future. Your devices are literally already living in it. So, what do you think comes next?